In this lecture, we discuss about the ordinary simultaneous differential equation. So, what is the ordinary simultaneous differential equation? So, to define this equation, first we discuss how to obtain that ordinary simultaneous differential equation. So, let us consider the first order and first degree differential equation. For example, P1 dx plus Q1 dy plus R1 dz is equal to 0. So this is one more equation, first order and first degree differential equation. So we take another differential equation, that is P2 dx plus Q2 dy plus R2 dz is equal to 0. Okay. So these are the two simultaneous differential equation of first order and first degree. So if we solve those simultaneous equation by using Cramer's rule, then we get the ordinary simultaneous differential equations. Okay, we solve both equation here simultaneously, so we get the ordinary simultaneous differential equation. So this equation, what is the solution? The solution for dx, dy and dz, solving for dx, dy, dz. So what happened here? So that is, so what is the dx upon what? So that is q1 r1 determinant, q1 r1, q2 r2. So is equal to dy upon, so dy upon r1 p1 determinant, r2 p2 is equal to dz upon what? p1 q1 and p2 q2 here. So solve this determinant, we get here dx upon q1 r2 minus q2 r1 is equal to dy upon p2 r1 minus r2 p1 is equal to dz upon p1 q2 minus Q2 Q1. Okay, so this is, we solve this simultaneous differential equation for dx, dy, dz. We get this. So dx upon something, dy upon something, dz upon something. So here P1 Q1 R1 and P2 Q2 R2 are the functions of x, y, z. Okay, so these are also functions of x, y, z. So we say this is as a dx upon, so this is big P, P. So this is P. So dy upon Q is equal to dz upon R. Okay. So dx upon P, dy upon Q, dz upon R. So this where PQR are functions of x, y and z. Okay, so this equation is called ordinary simultaneous differential equation. So this is a it is easy to identify the ordinary simultaneous differential equation. So dx upon p, dy upon q, dz upon r. So how to solve that differential equation, that is important here. So what is the method of solving the ordinary differential equation? There are two cases, one general case and second particular case. So how we solve that equation? By using two methods here. Okay, so we take example. So what is the example is, and how to solve this differential equation. So what is the general particular case and what is the general case? So before that we take example. solve, and then we discuss the theory here. So solve dx upon yz is equal to dy upon zx is equal to dz upon xy. Solve this differential equation. This is the ordinary simultaneous differential equation solution. So we say this is a fraction. So this fraction is equal to this fraction is equal to this fraction. So something divided by another term here. So this is called a fraction. So this fraction is equal to this fraction is equal to this fraction. So how to solve this differential equation? So we taking first two fractions. Taking first two fractions. So what are the fractions? Dx upon yz is equal to dy upon zx. So dx upon yz is equal to dy upon zx. So z is cancelled here. Z is cancelled. Z cancelled. So what is remaining? Dx upon y. So that is implies that dx upon y. So dy upon x. Okay. So here one variable is absent. So which variable? So there are three variables x, y, z. Here z is absent. So what is the first step? We absent one of the variable of three variables. So we absent here z in three variables x, y, z. So this is the differential, simple differential equation. So we separate the variables. So this equation can be written as x dx is equal to y dy. Okay. So then what is the after integration? On integration we get, so what is the integration of x dx? So that is x square by 2 is equal to y square by 2 plus integrating constant c1 here. Something c. Okay. C1 constant here. Okay. Therefore, what is this? So x square upon 2. So that is x square upon 2 minus y square by 2 is equal to c1. So this is equation number 1, which is one part of the complete solution, which is one part of the complete solution. So what is the another part of that solution, complete solution? So another part is what here? So we taking another fractions and absent another variable. So we take first we take the first fraction and third fraction, or you can take last two fractions. Okay. So taking last two fractions, then what happened? Taking last two fractions. Then what happened? So that is dy upon zx is equal to dz upon xy. So this implies that, so x get cancelled, so what is remaining there? So dy upon z is equal to dz upon y. So what is this? So here x variable is absent. In this fractions, z variable is absent. Here x variable is absent. So this equation can be written as y dy is equal to z dz. So on integration, so this implies that on integration, so this is y square by 2 is equal to z square by 2 plus c2. Okay, therefore this is equation number 2 here. So something you can write. So y square by 2 minus z square by 2 is equal to c2. So this is another part of the complete solution. So this is another part of this complete solution. The two solutions taking together, the solutions solutions 1 and 2 taking together is the complete solution. Okay, so this is a very simple method to solve by solving the ordinary differential equation. Okay, so this is a particular case, means you take any two fractions and absent one variable and then solve it. So this is one part, and you take another two fractions and absent another variable and solve this equation, taking another part of the differential equation. The two solution taken together is the complete solution. So this is the particular case to solve this differential equation. Okay, so we take another example here. Solve dx upon y square. So dy upon x square. So dz upon x square, y square, z square. Solve this differential equation. Okay. So again, we take two fractions. So taking first two fractions, first and second fractions. So we get here dx upon y square. So dy upon x square. Okay. So this equation can be written as, separate the variables, x square dx is equal to y square dy. So on integration of this equation we get, so on integration what happened? So this is x cube by 3 is equal to y cube by 3 plus something constant c1. So this is one part of the complete solution. This is one part of the solution. So we take for the another part, we take another two fractions here. We take first and third or last two fractions. Taking last two fractions, so what happens? So dy upon x square is equal to dz upon x square, y square, z square. So what happened here? So this implies that x square get cancelled. So what happened? So dy is equal to dz upon x square get cancelled. So this is y square, z square. So this equation can be written again. This implies that, so y square dy is equal to dz upon z square. Okay, dz upon z square. So what is on integration? So on integration what? On integration so this is y cube by 3. Integration of y square dy is equal to y cube by 3 is equal to, so this is minus 1 upon z. So what is the integration of 1 upon z square? Because what is the derivative of 1 upon z square? Is minus 1 upon z square. Minus plus. So integration of this dz upon z square is minus 1 upon z plus integrating constant c2. So this is another part. So this is equation number 2. Okay. This is another part of the complete solution. The two solutions 1 and 2 taking together is the complete solution. So this is simple method to solving the differential equation. But there is a problem. We can't each example solving by this method. So there is another methods. So there are we taking here the example, two examples, and solving those examples by particular case. So absent one variable in first part and absent second variable in second part, and solve those equation, and two solution taking together is the complete solution here. So what is the second method to solve this differential equation? So ordinary differential equation, what is the general case? Okay. General case. So what is the differential equation? So the standard differential equation is dx upon p is equal to dy upon q is equal to dz upon r, where p, q, r are functions of x, y, z. So this is equation number 1. So this is the ordinary simultaneous differential equation. Okay. Let L, M, N and L dash, M dash, N dash are two sets of multipliers. So we choose two sets. So this is first set, this is second set. So let Lmn and L dash, M dash, N dash are two sets of multipliers. And can be written as and can be written as. Then what happened here? So that is dx upon p is equal to dy upon q is equal to dz upon r. So this can be written as. So what happened? So we take first set of multipliers Lmn. So we multiplying L to this, also to this, multiplying L, M, N also to numerator and L, M, N also to denominator and adding them. Okay, so L dx plus M dy plus N dz divided by LP, multiplying LP also, LP plus MQ plus NR. Okay, so taking this multipliers here. So is equal to, also we take these multipliers, multiplying corresponding terms in numerator and denominator and adding them. So that is L dash dx plus M dash dy plus N dash dz divided by L dash p plus M dash q plus N dash r. Okay, so what happened here? So dx upon p, this is a fraction, so this is a fraction, so this is a fraction, this is also one more fraction, so this is also another fractions. So you make it so many fractions, infinite fractions are there. Okay, so this fraction is equal to this fraction is equal to this fraction. If we can't unable to solve the differential equation, you make more and more fraction, then solve the differential equation. So that is one more method here. Okay, so let us choose Lmn in such a way that so Lmn in our hand, those multipliers in our hand. So we choose Lmn in such a way that what happened here? So Lp plus Mq plus Nr is equal to 0. So we choose Lmn such that Lp plus Mq plus Nr is equal to 0. So this implies that, therefore, this implies that this is also 0. So L dx plus M dy plus N dz is equal to 0. Okay? So we get a very simple equation. So on integration, so solving this differential equation, first order and first degree differential equation. So solving this differential equation, what happens? So we get the solution u in bracket x, y, z. So this is a function of x, y, z is equal to something c1 is the constant here. So that is equal one part of the complete solution. One part. Okay. So this is one part of the complete solution. So we choose another set of multipliers. Let us choose. Let us choose L dash, M dash, N dash. Another set of multipliers in such a way that what happened? So L dash P, M dash Q plus N dash R is equal to 0. So this becomes 0. So we choose LM, L dash, M dash, N dash such that this is equal to 0. So this is those multipliers in our hand to make this is 0. So this implies that. What happened? So this is L dash dx plus M dash dy plus N dash dz is equal to 0. So on integration what? On integration we solve this differential equation first order and first degree. So we get this solution in this form. So function of xyz is equal to C2. So this is another part of the complete solution. So this is one solution, this is another solution. Those two solutions taken together is the complete solution. The two solutions 1 and 2 taking together is the complete solution. So here the theory is very simple here. So how to solve the simultaneous differential equation by taking set of multipliers. Okay. So we take example. We take a very simple example taking here. So that is solve example. Solve dx upon mz minus ny dy upon nx minus ly and dz upon ly minus mx. So solution. So we can't take any two fractions because it is difficult to absent one of the variables of x, y, z. We can't any two fractions, this fraction or this. So previous method. Okay. So we can't any two fractions, and it is unable to cancel or absent one of the variables. So we solving this differential equation by another method. So that is general case. Just we discuss about that here. Okay. Let us choose the set of multipliers. Choose the multipliers. Elements such that in such a way that elements such that so each fractions is equal to each fractions. What is these fractions? So these fractions means each fraction. So it is not necessary to write here this is equal to something. Not necessary. Just you write each fraction is equal to. So each fractions means this. So what are the multipliers? Element. So that is L dx plus M dy plus N dz divided by what happened? L mz minus ny plus M nx minus ly plus N ly minus mx. Multiplying to numerator and denominator to the fractions and adding them, we get this. Okay. But what happened? So this is what? So this is L dx plus M dy plus N dz divided by. So what is this? So this is equal to 0 here. Why? LMZ. So LMZ is what? Where is L? So just a minute. LMZ. So LZ here. LZ, I think. LZ. Okay. So this is LMZ. So this is minus LMZ. So that minus LMZ and minus another LMZ. So each term gets cancelled. So this is equal to 0 here. This is equal to 0. So this implies that. So L dx plus M dy plus N dz is equal to 0 by using theory here. Okay, by using theory. So this is very simple one. Okay, okay. So if this is 0, then this equal to 0. So on integration, what happened? What is the integration? So this is what? Lx on integration. Lx plus My plus Nz is equal to C1. So this is one part of the complete solution. Okay. This is one part of the complete solution. So okay. So now we take another set. We choose. Let us choose another set. Another set. X, Y, Z. We get in such a way that X, Y, Z. We get. So that is each fractions is equal to. Each fractions is equal to. So multiplying here X, also X, Y, 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 Z, Z. Adding a numerator and denominator, so that is X dx plus Y dy plus Z dz divided by. What happened? X into mz minus ny plus y into nx minus lz plus z into so ly minus mx. So then after simplifying this, so we get this is 0. So therefore x dx plus y dy plus z dz divided by 0 here. And this implies that, so this implies that x dx plus y dy plus z dz is equal to 0. Okay. So on integration of this. So what happened? What is the integration of this? So that is x. Integration of this is x square y 2 plus y square y 2 plus z square y 2 is equal to C2. Okay. So this is another part of the complete solution. So solution, this is one part, this is two part. So taking two solutions. Taking two solutions. 1 and 2. 1 and 2 is the together, taking two solutions together. Is the complete solution. Is the complete solution. Okay, so in this lecture we discuss, so what is the simultaneous differential equation and how to obtain that equation. So what is the formation of that equation, and we discuss here two methods. So that is a general case and particular case, and taking example examples. So in the next lecture we take examples and what is the geometrical representation of ordinary simultaneous equation, differential equation. Okay, so we stop it.